Hi, I'm Mauricio. I work with the GATK team as well. I will talk to you about parallelism. So Chris just said we're done with the whole pipeline, and it's true. So what I'm going to do now is just tell you this neat little trick that you can actually do to make everything faster. This talk is going to be about how can you use the GATK in a parallel environment. And we know there are several different types of parallel environments out there. This is really supposed to be an overview. And if you want any more details, I'm happy to answer after the talk and the questions. So like every other talk here, it starts, where are we in the pipeline? And the answer is we are everywhere in the pipeline. Most of these tools will be enabled to run in parallel mode, in one of the many parallel modes that we have. Not all of them, but most of them do. Some of them in multiple parallel modes, and we'll see how we can use this. So what is parallel compute? Parallel is basically the new faster. The chip makers have stopped trying to double the speed of the processors every new iteration. Instead, they're just packing more and more cores inside a single chip. That's really where the manufacturers are going with. And the last decade, the software development has also shifted to attend those demands. So instead of just running the algorithms on a faster computer, to make them faster, we now have to recode our algorithms to work in this parallel environment. Also, with the with the cost of compute getting cheaper and cheaper by the day, compute clusters are ubiquitous today. Either your institution already has a compute cluster, a big data center, or you can just log into the cloud and rent out compute from Amazon or Google or any of the clouds out there and use hundreds or thousands or infinite compute. So to actually make use of that, the programs have to change. And the good news is that the GATK doesn't have to change because from the beginning, it was designed to be parallel. It is intrinsically parallel. It's built over a MapReduce framework, which I'll talk a little bit about. This is more of a programming details that are not important. But the GATK was built from the beginning such that any tool, any algorithm that you write on top of it will automatically, unless you know otherwise, parallel. So in this module, we'll see how to use this parallelism in the GATK. So there are basically two big classes of parallel compute out there. One is the shared memory parallelism, and the other one is the non-shared memory, where each compute has its own memory. The shared memory is usually the one that you run on your own computer, or it could be a large machine, it could be a server that you log into, and the program is running in that machine completely. So all of the data, all of the tools, all of the programs that you're going to run, even if you're running a large pipeline, are going to be loaded into the memory of that compute, or by memory, I'm just simplifying here, but it could be just a hard drive, the paging, swaps, and et cetera. But it's all loaded into that computer. All the resources are available to that computer. And that computer, since it's modern, it has multiple cores or multiple CPUs with multiple cores each. And all of these CPUs and cores will make use of all the resources internally. From a computer science perspective, coding in that environment is complicated because you have to make sure that when one CPU changes anything in the memory, the other one knows that this was changed and doesn't make a mistake. It's a very tricky environment to work on, but from the user's perspective, this is the simplest because all of the resources are available. You don't need to scatter your resources around the network and put them all back. It's all in there. You just push a button, and basically the operating system does the magic. So this is one of the types of parallelism. For that type, programs have to be written specifically to run in that way. You can't just take any program and say, now run in parallel, because it's not programmed to work in that environment. The other type of parallel compute is what we call the cluster or cloud. Basically, it's a non-shared memory. So here is when you have hundreds, thousands, millions of computers, and you have a program that may or may not be designed to run in parallel. It doesn't matter. Now what you do is you yourself just slice the data in many ways that you know are okay with your analysis, and then you send parts of this data with the entire program and the resources necessary to each one of these compute nodes, right? So in the picture here, we have just a generic data center with many, many blades of computers in there. And you're basically sending your entire data set and the tools that you're going to run to each one of those nodes. And then, as an orchestra, you're going to say, now run, everyone. And they will all run, they'll all do their own thing. And from their perspective, each one of these nodes only see and are only processing whatever you told them to. So this is basically, from their perspective, they're running on a single machine, on a single core. Maybe you're combining the two, maybe you're doing shared memory parallelism in each one of these nodes, but that doesn't matter. From their perspective, they're really running the whole thing internally. They will produce an output, each node will produce an output, and then it's on you to combine this output. So this is a fairly sophisticated trick to make every program out there sort of parallelizable. I'm saying sort of because it still depends on you as an analyst being able to split your data like that, analyze it like that, and then combining it like that. Some programs really need to see the entire data and process it all at once. It happens. So for those, you will still not be able to do this. But for other programs, for most programs, you can, at some level, split your data and run it in parallel using a cluster. So as I just hinted, you can also combine the two, right? Each of these nodes can have multiple cores, and you can, inside each node, run with shared memory parallelism, given that your program allows you to do so. And this is what we do here. Every time we talk about GATK, we were talking about shared memory or cluster runs. We never think about a single run. We never run the GATK on a single CPU, and I hope you don't either. So these concepts are key and are very important, and that's why we decided to include this into the workshop. So how do we use this in the GATK? So the GATK is actually two different beasts. There's the engine, where every input, all the BEM files, all the data, all the resources get loaded in, get organized, pre-processed, downsampled, and prepared such that it can be served on a tray to the walkers. So the walkers are now these programs that we build to process the genome or do something to the genome, do some analysis, perform some method or analysis into the genome. The methods don't have to deal with all that, the pre-processing, the loading, the scheduling of the files, handling thousands and thousands of files, databases. The walkers just look at the pieces of data that come to it, do whatever it's supposed to do, the algorithm runs, and then it produces a intermediate output. The engine is in charge of giving it on a tray, beautifully organized input, so that it can process, and then taking the output and combining in the end to produce you maybe a BEM file, maybe a VCF file, maybe whatever file you want to generate with the GATK with your walker. So this is not a programming course. If it was, we would be talking about the two in very different ways, but the walker is basically what a GATK programmer will write. So if you want to write your own analysis tool, you will be writing a walker. If you, let's say you want to write a program to select all the variants that are present in one family but not in the other one. That's a very, very simple walker to write. It's like 2 or 3 lines because the engine already did everything for you. You already parsed the files, took all the different BEMs, put them together, split them into the different samples. So as a walker, you can just say, I want those samples, not those samples. They're all already in the same ordering, and I can just produce the output. So this is important because we have built-in parallelism inside the engine. Therefore, any walker that we write can be, as long as it's possible, can be intrinsically parallelizable. So this is a very good depiction of what the GATK is like, except that the walkers are a little bit faster than that, even on single CPU. But we do strive to make them faster and faster. And with parallel compute, they do look like that. And so this is a better, more accurate picture of what the GATK looks like. And what happens is we have 3 different ways to parallelize. These are built-in methods. We could, in practice, add more inside the walkers, but these are the 3 ways in which the GATK can be parallelizable. And different from the other talks here where they were talking about many programs sometimes, or sometimes one full program with many, many, many command lines, this entire talk is about 2 command line options. And the 2 command line options are -nt and -ntt, and I'm going to talk about those, and I'll talk a little bit about Q. So this is an oversimplification. This is really simplifying what it actually is happening under the hood. I'm just trying to make a concept simple to understand, but I'm happy to talk in more detail if you want to. The Dash NT is when you're thinking about parallelizing at the engine level. What's happening here is that you're taking all that pre-processing and say, well, you can go ahead and spawn different, use different cores to pre-process and load and schedule all these files in different regions, contiguous regions, but in different regions at the same time. So this core will process this entire slice of the data. This other core will do this entire slice of the data, but these are still contiguous, and the results will come in order. These different slices will be processed by their own walkers, and then the engine is still in charge to combine all the results and produce just one output. Right? So this is conceptually parallelizing at the engine level. Of course, the walker is also parallelized in this fashion, but what in essence, what you're doing is you're taking the data and telling the engine, well, partition it this way and run the entire GATK this way. For the -NCT option, that's a little more subtle. This means that the walker itself is having its part of its processing, the map part of its MapReduce framework compute, being parallelized. So the engine is serving all this data, and the walker itself is being spawned multiple times into all these different cores, and the engine is just serving them all little pieces, saying process this, process this, process this, process this, and as the results come back, the engine just takes and gives it the next obvious piece of the data to process. So this is still traversing the genome in a contiguous fashion, but the walker, you can imagine there are many walkers, and the engine is just serving them in parallel. So that's the -NCT option. Both of these options, and I'll just cut here a little bit, because both of these options are supposed to be in-memory parallelism. So these are all supposed to be, sorry, not in-memory, shared memory parallelism. These are all supposed to be happening in one machine, and your machine or server machine, and the only option you have there is to say how many ways parallel you want this to happen. So if you say -NT4, you're saying use 4 cores to process my data. Same thing for -NCT. Some tools are available at end-NCT, which is a little bit more sophisticated, but most tools are available with -NT. Some tools are available with both of them. In fact, most tools that are -NCT-able are also -NT-able. So there's nothing telling you that there's nothing limiting you from using one or the other. You can actually use both as long as the tool was designed to do that. The other type of parallelism is what I was explaining in the cluster way. So if you don't want to do an in-memory, shared memory parallel system, you have a lot of computers out there, and you want to send all your data to all these nodes and get them back. Well, the GATK has this companion tool called Q that does that for you. So Q takes care of all the management of splitting the data, sharing it, scattering it through all the nodes, running the GATK entirely from end to end. Even if you have a pipeline of many tools that have to run, they will all run into its own nodes. Then it gathers the output of each one of the nodes, combines them all in a way that is compatible with what the tool decides, what the tool needs for the combination, and gives you one single output. So Q does all the magic for you, such that you can push a button and have everything sent into this magical cluster, get all parallel processed and returned to you. Q is a great tool. It was developed for us to use. We never meant to distribute it for other people to use, but it's just so useful that, well, you should very well use. There's a lot of people using Q. It's built inside the GATK, and there's a lot of documentation for it. So, as I've been saying, the walkers itself, or any program, needs to be reprogrammed in order to use the shared memory parallelism. And the different walkers that we have in the GATK will be able to use different types of parallelism. The type that is amenable to, yeah? Sure.
I'm an end-up user. I'm not going to develop any of this.
Yeah.
How do I know which one of these I can use in my machine?
Fantastic. The answer is here. To know which type of parallelism you can use for a given tool, you have to visit the website. Because each tool will be amenable to one type or the other. Each tool has its own types implemented into it. And In the GATK docs, which is how we call our documentation for each tool, if you go into the website, guide, technical information, there's a list of all the walkers there. When you click on any walker, it'll tell you how can it be parallelized. It can be used with -NT, it can be used with -NCT. Or if you go for Q, it can be partitioned one way or another way. I'll talk about that in a minute. Okay? Yeah.
But so to understand like what the optimal number is for NT or for NCT, you have to understand, I guess, your machine, how many processors cores.
I guess that's $1 million question. It'll really depend on a lot of things. The optimal number will depend not only on your machine, the resources, how fast can it access the RAM, how many, but also on the tool, how many consecutive concurrent access is it making to the same data source, as well as the whole GATK engine. Because every time you're parallelizing, especially with SNT, you're creating more and more engines that are parsing the data more and more. So each one of these things come with a little bit of overhead. This is not free parallelism. It's not just I had 2 things to do and I'm giving it to 2 people. No, I had a lot of things to do. Some of them can be parallelized. Others I still have to do again for each new node that I spawn. So there is overhead in every time you parallelize. So you really want to still have a lot of work to be done per core, per instance, per compute. Otherwise, you will be bottlenecked by all the overhead that you have to prepare for that core to start to be used. There's no magical number. If there was, we would not even have this option. We would just do it automatically. There's no magical number. It depends on the tool, it depends on your machine, the resources, what's being used right now on your machine, what's running, other programs. But yeah, you can always test if you're redoing this. Yeah.
We do have a table of recommendations for the best practices.
Right. We do have this table of recommendations, but those, like I'm saying here, it's very generic. If you have a 64-core machine, the -NT2 recommendation is definitely not the best for you. You could probably go a little bit higher, depending on how big your data is as well. So we do have recommendations, but ultimately you'll have to find it on your own, which one is the best numbers to use, which ones are the best numbers to use. So most GATK walkers are parallelizable. They're most of them, if not, it's almost every single one of them are at least able to run in parallel with Q. Yeah, almost any one of them can be run with Q, at least at the chromosome level. We'll talk about the different ways in which Q can slice your data. At the chromosome level, it's usually the one that you can always trust will work well, but there are other ones. So when I said Q can slice your data, and I think this is a very important, it's important for you to understand when you run Q, what exactly are you doing? It's not just a magic button that will make things faster. You really have to understand how your analysis is being split. The tools themselves know how they should be split, so they will tell Q. So you can be sort of insulated from this, but it's important for you to understand how things are being split. So there are basically 3 ways to split your data. By contig, which means each chromosome, entire chromosome, or if you have an extra contigs, will be processed independently. So you cannot cut in the middle of a chromosome. It can only cut different chromosomes and send to different nodes. So each node will process an entire chromosome. That way, it usually has, for most of the tools, all the information it needs to get the full answer. Usually, for most tools, it doesn't matter if it's only seeing chromosome 1 or chromosome 20. It'll do the full algorithm. It'll give you the same answer. So usually, that's the safest option. That's the one that almost every tool can run. By interval, that's when you're doing something like an exome or some things or you're just cutting genes separately, or you have regions of interest that are completely independent from each other. Some tools are capable of analyzing just that region and producing the same result as if it had the vision of the whole genome. And by locus, that's the most splittable option of all. That basically means that all the tool needs to see to make the decision is that one locus. And with that locus, it can make the full decision. And therefore, you can cut your data any way you want. Some tools, like the unified genotyper, can be split by locus. So just a few minutes here, I want to talk about going beyond parallel. So this is just what have we been doing here at the BroadE keep up with the pace of innovation and the next levels of parallelism that are available out there. So some of our tools, we are looking at implementing them into alternate parallel levels. And two of them are FPGA and GPU. FPGAs, or field programmable gate arrays, are basically a different coprocessor that you put on your machine. So it's a different architecture altogether that works with the CPU and memory and everything to do parallel compute when necessary. And the GPU, most of you probably already know, are just graphics cards that if you play video games, you have a really good one in your computer. If you don't, you will still have a pretty good one in your computer because all the new computers come with them. They have millions, thousands of CPU cores in there. They're not full CPU cores, but there's thousands of cores that can do a lot of compute in them as long as you program for that. The FPGAs have a completely different architecture. It works with gates. It has millions and millions of gates in each chip, which gives you, on the latest implementation, hundreds of processing units, processing elements that you can also use. It has the advantage of having a very fast input-output communication with the memory via this bidirectional data buses. And it has a somewhat large memory to do so compared to GPUs. GPUs are a little limited in the amount of memory they can do, but GPUs have the edge on fast double precision calculations, which for some tools and for some things that we do are critical as well. So those are two very important new technologies that are around. People are using it all over, and we thought it would be interesting to test at GATK and implement tools for that as well. So I'm not going to go into the details of the implementation of this, and just to give you an idea of what has to be done so you can harness the potential of these technologies. We have inverted the calculation of one of the key parts of the haplotype caller to see if we can make it faster. So typically, this is where we compute the differences between a given haplotype, a potential haplotype that we're trying to evaluate, and the read that we're evaluating. We do this hundreds of billions of times when we run the GATK haplotype caller. And making this fast is definitely going to cause a huge impact. In the CPU implementation, when you're running this in the CPU of the haplotype caller, this entire matrix here of differences is computed cell by cell, one at a time, serially. When we go to, because there's not even enough cores in one machine to make this even interesting. If we could parallelize it all, we could use 8, 12 CPUs. That's not really interesting. But when we move to GPUs or FPGAs, we are now able to process the entire thing in parallel. We can, in fact, there are 3 of these matrices, not just one. There's one for matches, one for insertions, one for deletions. They can be completely parallelized. And if we move to a diagonal implementation of this, which is called wavefront, all of the diagonal can be calculated in parallel because the values are not dependent on any of the previous or future values. So by shifting to this implementation, we can actually calculate the entire diagonal of each one of these read haplotype pairs in parallel using the hundreds or thousands of processing elements of these different technologies. And when we do so, this routine, which we call per-HMM, this routine itself, which used to take 3 hours to parse through 10 megabases of data in the CPU, now takes 8 to 10 seconds. The haplotype caller as a whole, so the haplotype caller is much more than just the per-HMM, got a very significant speed up. So these numbers you will never see because, again, we never run the GATK without being parallel and sending it to the cluster. But if you did, it would take approximately 10, maybe 15 days to run the entire haplotype caller on the NA1278 data set, whole genome deeply covered. But with the FPGA and the GPU, we got numbers between 20 and 72 hours. So this is only optimizing one routine inside the haplotype caller. So this is very promising. Both FPGA and GPU showed equivalent speed ups, which was very good. And these are both platforms that are available out there, both for purchase and for use in private clouds. You can just rent them out and use them to test it out. So if you do have a project that's very large data set, you can just go to Amazon, get an instance with the GPU and run the tools that are capable of running the GPU, and you'll benefit from all these improvements. There are also clouds that provide FPGA processors equivalent to Amazon. You can also go there and implement FPGA. So these implementations are already in the development version of the GATK. They will be available in the next version for everyone. And we will put this increase the support for both of these GPU and FPGA for other tools as we get the resources to do so. Before I finish, I want to say the development of those things were done. I actually had it here in the other slide. So the development was not done by this group alone. We had help from Scott Thibault from Green Mountain Computing Systems, who implemented the Impulse C version of the ParaHMM in the haplotype caller. This was also done in collaboration with George Vasek, who is here. If you want to talk to him, here he's right there. He's at Convey Computer, one of the makers of the FPGA. So he's a very good resource if you have any questions about FPGA or how to obtain, where is the cloud that you can use these machines, he would be a good reference. And the GPU version was a collaboration we did in-house in collaboration with Diego, who's an expert in GPU implementations back in Brazil in the Institute of Pure and Applied Math. So yeah, I just want to finish saying that there is a full document too, actually, about the very thing that I talked here in the GATK website. There's a primer on parallelism with the GATK. And there's another one with how to write parallel walkers to the GATK, which I would love to give this talk, but maybe for a different workshop. That's the second entry right there. Entries for FPGA, GPU, the MapReduce framework, and Convey Computer are there. If you have any questions, I'll be happy to answer. Yes?
So what's the slowest step in the whole GATK pipeline? And how long does it take to run the whole thing?
Huh. Yeah, I would say probably the haplotype caller right now. What is the slowest? I think it's the haplotype caller right now. And that's probably why we focused on the haplotype caller to do the first test of optimization using alternate compute infrastructure.
So it's alignment.
No, it's not alignment, no. Alignment's down to 7 hours for a whole genome, deeply sequenced whole genome. So alignment is doing pretty well. Because it's so well parallelizable. Alignment is one of those problems that you can parallelize as much as you want, and there's no overhead. Because it's basically you're just sending reads to different processors. There's no overhead in setting up new nodes. The Indel realigner is also very costly, but not as costly. So Indel realigner and base recalibration are also very costly. They're both very costly. They're both parallelizable. But I still think that the haplotype caller, you asked the most costly. I think the most costly is still the haplotype caller. Although we've been doing a lot of work to make it fast. If we were giving this talk 2-3 months ago, no question, haplotype caller. But now we've made it so much faster that it's starting to get close to the other tools as well. Yep.
Is it GATK fault tolerant, so if you split by chromosome and like node processing chromosome 2 crashes, you have to rerun all?
That's a very good question. So Q is as super powerful as the name implies, if you're a Star Trek fan. It's a very powerful tool. So it does take care of fault tolerance. So if one of your jobs fail for any reason, maybe the machine turned down or the hard drive broke down, it'll know that that's the one that failed, and it'll tell you everything finished but this one or 3 or however many failed. And if you rerun, it'll only rerun the ones that failed and continue where it stopped. So even if your pipeline had 20 tools to run from end to end, and tool number 13 failed on 2 jobs, it'll continue from tool 13, 2 jobs, and go all the way to the end. So all of this is built into Q. And just taking your opportunity on your question, going one step beyond, the other way in which we could be making mistakes would be by splitting the data in a way that's not supported by the walker. Let's say a walker needs to see the whole chromosome to make decisions, like the Indel realigner. This cannot happen in Q because the tool tells Q how to split the data, right? So the Indel realigner, for example, will say I can only be split by chromosome, and then Q decides. You tell Q how many nodes you want to use, and Q will split your data according to how the tool can be splittable. Any more questions? Well, I'll be here if you want to ask any more questions, and George is also around if you want to talk about FPGA. Thank you very much.